Hello, everyone, and welcome to the Algebra 3 Unit Test 3 review. So as I go through this, please understand that this is not a comprehensive review, and you're still going to need to study all of your notes, assignments, quizzes. All of that's going to be super beneficial as we go into this test. So please make sure you are studying, and we're going to go ahead and jump right in. So the first thing we want to do is describe end behavior using the proper limit notation. The proper limit notation is when we say, a little too thick. Okay, when we say the limit as x approaches negative infinity, that means we're going to the left. F of x equals, and we want to figure that out. And then the limit as x approaches a positive infinity, f of x approaches what? So the first one, this is essentially saying the left side, and this is essentially saying the right side, but that is the correct notation for it. And you need to make sure that you are writing that all the way out and not missing anything, including the limit, the approaches, all of that fun stuff. From there, we need to take our highest degree term, which in this case is negative 4x to the fourth, and we need to determine our end behavior. So the fact that this is negative out front, it's a negative leading coefficient, that is telling us that our right side is going down. So when it's negative, that means that our right side is going down. And the fact that it is even, that tells us that our left side is going to be matching our right. So our left side is also going to be going down. So that means for this first limit notation, f of x is approaching, not infinity, negative infinity, because that's what it means to be going down. And for this second one, which is our right side, that's also approaching negative infinity because the right side is also going down. So that is how we would denote that. Moving on to the second one. Again, we're going to write this in limit notation. So the limit as x approaches negative infinity, f of x equals. And the limit as x approaches positive infinity, f of x equals. Again, this represents the left side of our graph and the right side of our graph. Okay, and those will never, ever, ever change. That should always be written. From there, we need to determine what our end behavior is going to be. So we need to determine our leading term. So to do that, we take the highest degree term of each of our factors, including its coefficient. So we would take negative x to the third time, because that's the highest degree term from the first factor. The next highest degree term from the second factor is just a regular x. And the third term gives us the term of x. So that means our leading term is negative x to the fifth. So again, because it is negative out front, that is telling us that our right side is going down. And because it is an odd degree, that tells us that our left side is doing the opposite of the right. So our left side is going up. So in our limit notation, for the first one, as x approaches negative infinity, f of x approaches infinity, that's our left side. And in our second one, as x approaches infinity, that's our right side, f of x approaches negative infinity because the right side is going down. And so that is how we would properly denote limit notation and end behavior. Okay, now we're going to go ahead and state the possible number of real zeros and the turning points for each function, and then we are going to find those zeros by factoring. So the way we would determine the number of possible zeros, that's going to be from our highest degree of the entire polynomial. So the number of possible is just 3. And then the number of turning points is gotten by taking that 3 and just subtracting 1. So that would be 2. Okay. And from there, it says we need to factor. So the first thing we always want to check for is a GCF. So the greatest common factor from all three of these terms, the biggest number that we can take out is just going to be an x. So that'll leave us with x squared minus 7x plus 12. And from there, we can factor the rest of this using the box. So we would put x squared here and 12 here. We'd multiply those two together. So that's 12x squared, and it needs to add to a negative 7x. After thinking about those factors for a second, hopefully you get that that's negative 3x and negative 4x, and you can check that. Negative 3 times negative 4 is 12, and negative 3 plus negative 4 is negative 7. Out of the first row, you can take out an x. Out of the second I'm sorry, out of the first column, you can take out an x. Out of the second column, you can take out a -3. Out of the first row, you can take out an x, and out of the second row, you can take out a -4. So this entire thing factors, and we cannot forget that greatest common factor. You have to bring that down. So x times x minus 3, x minus 4. And that is how we would write it in our factored form. Okay, so if it asks us to find it in our factored form, that's how we would do it. And then it wants us to find the zeros. So that means we're going to take each of these factors and set them equal to 0 and solve. So for this first one, we already have that x equals 0 as a solution. For the second one, we would add 3 to both sides and we get that x equals 3. And for the third one, we would add 4 to both sides, and that would give us that x equals 4. So all 3 of these would be part of our solution. And that's how we would complete this problem. Okay, and we want to double check that we've done all our steps, state the possible number of real zeros and the turning points, then determine all of the real zeros by factoring. We've done that. Okay, so now let's do it for number 4. So again, we take highest degree, which is 5, and that's going to tell us the number of possible real zeros. So that means that there is 5 possible real zeros, and then we just subtract 1 to get the number of turning points, and that would be 4. And from there, we can factor. So again, we first want to start by checking our GCF, and all 3 of these have an x to the third in common. So we're going to go ahead and factor that GCF out. And so that would leave us with x squared plus 8x minus 20. And again, from there, we can use the box in order to factor what's inside those parentheses. So we have x squared and -20, sorry. So it would multiply to a -20x squared, but needs to add to 8x. Think about that for a second, and hopefully you should get 10x and a -2x. Out of the first column, we can take out an x. Out of the second column, we can take out a 10. Out of the first row, we can take out an x. And out of the second column, because the closest box is negative, we can take out a -2. So this should factor to x to the third times x plus 10, x minus 2. And so that would be our factored form. And then from there, we need to find our zeros. So we'd set x to the third equal to 0. So what that's going to give us is that x equals 0, but this degree of 3 is telling us that that 0 is happening 3 times. So the way we write that is 0 mult. It is a multiplicity of 3. Okay, so that's going to be one of our zeros. So make sure you are including multiplicities here. So we'd subtract 10 from both sides for this one. And so we'd get that another one of our zeros would be -10. And for this third one, we would set it equal to 0, add 2 to both sides, and we would get that x equals 2. So our zeros in a list would be 0 mult 3, -10, and +2. Okay, so do not forget your multiplicities there. Okay. Moving on to the next one. Again, the first thing we always want to check is greatest common factor. Well, actually, sorry, we want to state the number of possibles. Okay, and the number of possibles is related to the highest degree, so it'd be 4. Then we state the number of possible turning points. And that is going to be 4 minus 1, which is 3. And from there, we can factor. So hopefully we notice that there is not a GCF here, but we do have 3 terms. And so because of that, we can actually jump straight to the box. But this time we're going to be doing the box with an x to the 4th rather than an x squared. So we want something that multiplies to 9x to the 4th, but adds to a -10x squared. Okay, so the 2 numbers that do this, hopefully once you think about it, you're going to get -9x squared. It's not just going to be x, okay? You need to make sure you're being very careful about that. It's -9x squared and -1x squared. And again, that's going to multiply to a +9x to the 4th, but add to a -10x squared. So we're going to double check ourselves with that. Then out of the first column, I can take out an x squared. Out of the second column, I can take out a -9 because the closest box is negative. So we're taking out a negative. Out of the first row, I can take out an x squared. And out of the second row, I can take out a -1 because the closest box is negative. Also, as a gentle reminder, we always want our leading term to be positive whenever we're factoring. If it's not, we take out a negative GCF. So just make sure you're getting your first term positive before you throw it into the box. So this would factor into x squared minus 9, x squared minus 1. And hopefully we notice that both of these are difference of squareds. So x squared minus 9, we would take the square root of the first term, which is x, plus the square root of the second, which would be 3. Square root of 9 is 3. And we would do the same thing, but with subtraction. Okay? And then for the second one, the square root of the first term, which is x, plus the square root of the second, and the square root of 1 is 1. So we'd say x plus 1, x minus 1. And so this would be our factored form. Okay, and then from there, we set each of these equal to 0, and we solve. So we'd subtract 3 for this first one to get that x equals a -3. We'd add 3 to this second one to get that x equals a +3. Subtract 1 to get x equals -1. And I'm running out of room, so I'm going to do it over here. Add 1 for that last term to get that x equals a +1. So all 4 of these would be our answers. So we actually had the same reals as the number of possible reals. Okay, moving on to number 6. So again, number of possibles is determined by that degree. That degree is 4. Okay, and then for the number of turning points, we just take that and we subtract 1. So that's going to be 3. Okay, so now we want to factor. So we don't have a greatest common factor that we can take out of both of these. And so our next step would be to do difference of squareds because we have 2 terms. If we had 3, we would do the box, but because we have 2, we're going to do difference of squareds. So the square root of the first is x squared plus the square root of the second. The square root of 25 is 5. And then we would do the square root of the first, which is x squared, minus the square root of the second, which again is 5. Okay, so we got this far, but we need to go a little bit further. So if we wanted to factor this all the way out, we should hopefully see that this second factor is also a difference of squareds. Okay, but we're going to be dealing with some radicals. So the square root of the first term is x plus the square root of the second, which would be radical 5. That's what I'm doing here. And then the square root of the first, which is x minus the square root of the second. Okay. Now, if you wanted to factor the first one, you can, but because it's addition rather than subtraction, you're going to be getting, this is a sum of squares rather than a difference. And that just means you're going to be incorporating an I. So this would actually factor to x plus I radical 5, x minus I radical 5. Okay. But this question just asked us to determine all the real zeros. So we don't really need to solve for those imaginary ones, but I did want to write down that is how we would get some imaginary zeros here. So we're not going to solve for those because they just asked us to solve for the real ones. But if you wanted to, that is how you would go about factoring that imaginary number. And that's what happens when we have the difference of squares, but instead of it being a difference, it's a sum. We include an I and essentially do it the same way. Okay, so I'm just going to set this x plus radical 5 equal to 0 and this x minus radical 5 equal to 0, and I'm going to solve those. So I'd get that x equals a negative radical 5. And I'd get that x equals a positive radical 5. And this is what I would write as my answer. Because again, it just asked me for the real ones. Rather than listing all of them. If you needed to list all of them, then you would also set those imaginary roots equal to 0 as well. Okay. Moving on to the next section. It says for each function, find the zeros, y-intercept, domain, state, and behavior using proper limit notation and sketch a graph. Okay. So to help you out, I'm still going to list out the possibles and the reals just for a little bit of additional help with that. Because I know some of us struggle with that. So Where do we want to start? Okay, so let's start by getting our zeros. That's what we'll start with, because that's what it lists first on the list. So in order to determine our zeros, we're going to set each of these factors equal to 0. So we have -2 x to the third. I'm going to set that equal to 0. And if I solve that, I'm going to get x to the third equals 0, which means that that's going to give me 0 mult 3. Okay, because this is going to be a root 3 times because of that degree of to the third. So that would give me 0 mult 3. If I set the second one equal to 0 and solved, I would get that x equals a +3. So that will go on my list. And if I set the third factor equal to 0 and solved, I would get that x equals -4. But because it's happening to the second power, that would be -4 mult 2. It's occurring twice. It's a multiplicity. Okay. So those all would be my roots. So again, when a factor is taken to an additional power, that's when we start to worry about multiplicities. So from there, that was the first thing on our list. We found the zeros, we're good there. The next thing it asks us to find is the y-intercept. So you can find the y-intercept a couple ways, but maybe the easiest is just to plug in 0. So we'd get -2 times 0 to the third times 0 minus 3 times 0 plus 4 squared. So don't let the setup fool you. You're eventually going to be multiplying everything by 0. And so when you do that, you're going to get 0 out, because this would be -2 times 0 times -3 times 4 squared, which would actually be 16. But this is still going to equal 0 at the end of the day because you're multiplying one of these numbers by 0. So don't let that trick you. So really, our y-intercept is just going to be 0, 0, because you plugged in 0 and you would get out 0. Also, another way to see that this is 0, 0 is we already have a 0 as a 0 or root on our list, and that means that our y-intercept is the same as an x-intercept. So that all works out nicely. We'll state the domain in just a second once we start to graph it. And we want to state the end behavior next. So end behavior, just going to abbreviate it EB. So we want to find the highest degree term. So the way we do that is we take the highest degree term of each of our factors. So we take -2 x to the third. Okay. We're going to multiply that by the highest degree term of the second factor, which would be x. And we'll multiply that by the highest degree term of the third factor, which would be x, but it's taken to the second, so it'd be x squared. So our leading term is -2 x to the sixth. So what that's telling me is it's negative out front. So that's telling me that my right side is going down, but it's an even degree. So that tells me that my left is matching my right. My left is also going down. But this asks me to state it using proper limit notation. So we're going to go ahead and list that in limit notation. So we would say the limit as x goes to -infinity, f of x equals, this is as to the left, -infinity, because the left side is going down. And then we would say the limit as x goes to +infinity, it's going to the right. F of x would equal -infinity because the right is also going down. Okay, we're getting there. And then this also asks us to state domain. The domain of this polynomial function, because there are no restrictions on it, the domain is just going to be all real numbers or -infinity to infinity. You would also see that once we started to graph it. So let's go ahead and graph it. So we're going to draw a really rough sketch. We're going to plot our zeros. So that's going to be 0, 0. That's one of them. 3. So 1, 2, 3. Okay. And -4. 1, 2, 3, 4. Okay. So those are all the zeros on our graph. We also have our y-intercept. Okay, that's happening right here. And that's lining up with the 0 that we have. You should not have 2 y-intercepts. If you have 2 different y-intercepts, you've done something wrong. So make sure you're checking that. And then our end behavior says our left and our right sides are both going down. So we'll start on the left. It's going down. It approaches this -4, but see how this is a multiplicity of 2? Because that is an even multiplicity, it's going to bounce there and come back down. Okay, at 0, we have a multiplicity of 3. So that is what my students like to refer to as a swoopa. Okay, so that means we approach that root, we flatten out just a little bit, and then we keep going up. It changes its concavity rather than changing the graph, rather than changing the direction. So again, if you want to see it again, you approach, you flatten out a little bit, and then you kind of go back up. Okay, so please make sure you're kind of including that change in concavity. You can't just cross over and expect us to accept that because that's not showing that multiplicity. So you need to make sure you're showing the approach, the flattening a little bit, and then the coming back up. Okay, and then it comes back down, and we do not have any multiplicities occurring at 3. So it's just going to come back down and go back through. Your graph does not need to look exactly like mine, but it should look relatively close in regards to the multiplicities and the end behavior. And so that's how that graph would look. And again, we stated that the domain is -infinity to infinity. We can check that and we're clearly correct. Okay, moving on to number 8. So again, first we want to start with the zeros. Oh, one thing I did want to mention on the last one, in case you need extra practice listing the possibles and the number of turning points, because our leading term was -2x to the 6, we would have 6 possible roots and 5 possible turning points, right? Because we took that degree and -1. Okay, moving on. So looking at number 8, again, it's given to us in factored form. So to find the zeros, we'll set each of these factors equal to 0. So the first 0 we'll get is that x equals 5. But hopefully we see that that is happening twice because it has a degree of 2. So we will write 5 mult 2 because that is a multiplicity. And then we should also set the second factor equal to 0. And we'd solve to get 1. But again, that root of 1, that's being squared. So it's also a 1 multiplicity of 2. Okay, so those would be our zeros. Okay, now we want to find what was next on our list. We want to find our y-intercept. So to find our y-intercept, again, we are going to plug in 0. So that would give us 0 minus 5 squared times 0 minus 1. So note we're not multiplying by 0 in this situation. And also 0 was not listed in our list of zeros. So our y-intercept is not going to be 0, 0 this time. So we would have -5 squared times -1 squared. -5 squared is 25. And -1 squared would just be 1. So our y-intercept is just going to be 0, 25. Okay, and hopefully we know that a negative squared is going to be positive. Okay, so we got that. Now we are going to list our end behavior. Okay, and so our end behavior is going to be determined by our highest degree term. So we need to figure out what that is. So from our first factor, we have x, but it's being squared. So we would do x squared times, from our second factor, we have x, but it's also being squared, so times x squared. So that's giving us that our leading term is x to the 4th. Okay, this has a positive number out front. And so because of that, our right side is going to be going in the positive direction. Our right side will be going up. And it has an even degree. So that means that the left side will be matching our right and the left side will also be going up. Okay. And again, domain for this one, there's no real restrictions on this. So again, it's going to be -infinity to infinity. Oh, and we didn't write those in limit notation. Silly me, we need to do that. So we'd say the limit as x goes to -infinity, f of x approaches. This is a left side, so infinity. And the limit as x goes to a positive infinity, so the right side, f of x also approaches infinity because it's going up. And now we can graph. So we'll draw a little graph here. Okay, so our zeros are happening at 5. So 1, 2, 3, 4, 5. And also at 1. Okay, and this is saying the left and the right side are going up. Okay, and it also needs to cross at a positive 25. So this doesn't need to be perfect. We're just going to stick a point here. We're going to call that 25. And we're going to call that our y-intercept. So our left side is going up. So it needs to pass through. So actually, I'm just going to kind of draw it first, and then I'll determine the y-intercept. So, this line is struggling with me today. There we go. Okay, so our left side is going up. It's going to come down, and we see that we have a multiplicity at 1, and it's a multiplicity of 2. So that means we're going to bounce off of 1, come back up. We also have a multiplicity of 2 at 5, so we're also going to bounce off of 5 and come back up, and our graph will look like something like this. Maybe a little better. And then we just say wherever our graph crosses that y-axis, which is right here, we'll call that 25. Okay, does not have to be perfect, just has to be a pretty rough sketch. And so this is what our graph would look like. Okay, and we can double check our roots, double check our multiplicities, double check our zeros and our end behavior, but everything looks good. That is our graph. Okay, moving on to the next one. So these ones are given to you and they're not factored. So in order to find these zeros, we are going to have to factor these. Oh, also, again, for my people who want to practice the number of real, the number of possible real zeros, again, that's determined by the degrees, that would be 4. And the number of possible turning points, that is determined by taking that possible number of zeros and subtracting 1, so it'd be 3. Okay, the next one, so these are already written out for you, so we're gonna go ahead and factor them. So out of the first one, you cannot take out a GCF, and there's 4 terms, so that's a hint. We're going to jump straight to the box. Okay, so we'll put x to the third here, negative x squared, negative x, and 1. The box, when we have 4 terms, it kind of automatically fills it out for us, which is super nice. So out of the first column, we can take out an x. Out of the second column, the closest number is negative, so we're taking out a negative, and it's going to be just 1 because that's all they have in common. Out of the first row, we can take out an x squared. And out of the second row, the closest box is negative, and all they have in common is a 1. So far we have x minus 1 and x squared minus 1. But we can factor that second one further into a difference of squareds. The square root of the first term would be x plus the square root of the second. The square root of 1 is 1, and x minus 1. So you can leave this written like this. That's totally fine. Or just to be safe, if you want to write it as x plus 1 and then x minus 1 squared, that's correct as well. What I'm more concerned about in that sense is making sure we're writing the multiplicities. So we're going to find our zeros now. So we'd set x plus 1 equal to 0. Subtract 1 from both sides to get that x equals negative 1. And then we'd set x minus 1 equal to 0. Add 1 to both sides to get that x equals a positive 1. Okay. Sorry about that. Someone was calling me. Where was I? Okay, so anyway, we're adding 1 to both sides in order to get that. But when we're listing our zeros, we should hopefully see, so one of our zeros is a negative 1. One of our zeros is a positive 1. But it came from this square, so it has a multiplicity of 2. You could also see this if you had left it in this original form and you solved it, you would have gotten x equals 1 twice. And we write that again as 1 mult 2. Okay, so the nice thing about this one is determining the y-intercept is a heck of a lot easier because we can again go ahead and plug in 0. So we'll say f of 0 equals 0 to the third minus 0 squared minus 0 plus 1. And so all of this is just going to equal out to be 1. Because it would be 0 minus 0 minus 0 plus 1. So again, that's all just going to equal out to be 1. Oh, wrote 0. Good Lord. Okay. So our y-intercept is 0, 1. And then to determine end behavior, this time we already have the highest degree term given to us. That is x to the third. For my people who want to double check, the number of possible zeros is going to be 3. The number of turning points would just be 3 minus 1, which would be 2. Okay. And so because this is positive, that means that our right side is going up. It is positive out front, right? So the right side's going up. And because it is odd, the left side is doing the opposite. So the left side this time is going to go down. Okay, and writing this in limit notation, we would say the limit as x goes to negative infinity, f of x equals, that's to the left, we're going to negative infinity. Okay, and the limit as x goes to infinity, that's as our graph goes to the right. Our graph is going up, so it's going towards a positive infinity. So just make sure you're being careful with that limit notation there. Okay. And now we are going to go ahead and graph it. Again, domain, there is no restrictions listed here, so domain is still just going to be negative infinity to infinity. That's always a good thing to practice, is our domain. And we'll draw a little graph. I'm going to draw it off to the side. Okay, so we plot -1. We'll plot a point there. Plot +1, plot a point there. Okay, our y-intercept is 0, 1. So we can actually plot a point there because it's actually going to intersect pretty nicely at 0, 1 because we have a pretty tiny graph here. And then we'll draw our line. So this graph has the left side going down. So we're passing through -1, passing through that y-intercept. And again, we have a multiplicity at 1. So multiplicities of even numbers are when we're bouncing. So we come down and we bounce and we go back up. And so this is what our graph would look like. Okay. So again, make sure you know even roots are when we bounce, odd roots like 3. So even roots, like if we had x to the second, x to the third, I'm sorry, even roots, good Lord, where am I going? X to the second, x to the fourth, x to the sixth, and so on. All of those would be bounces. But when we have odd powers such as x to the third, x to the fifth, x to the seventh, those all would be the like approaches, flattens out, keeps going, the little shwoopa as we like to call it. Okay, moving on to number 10. Again, let's start by going ahead and factoring this. So as I said in a previous example, we have a negative out front as we're trying to factor. And that's going to make it really difficult to do the box, to do difference of squares, to do anything like that. So the easiest thing that we can do is when we go ahead and do our GCF, we take out a negative in order to get rid of that negative out front, make our highest degree term positive, and save ourselves a little bit of trouble. So I'm going to take out that negative. I can also take out of both of these terms an x to the third. So I'm going to go ahead and do that. And when I do that, I'll get x squared. And I took out a negative, so this is now -9. And that made my life a little bit easier in order to factor. So now I can, with this x squared -9, do difference of squares, because the square root of the first number will be x, and the square root of the second would be 3. So I can say x plus 3, x minus 3. Okay, so when finding my zeros, if I set negative x to the third equal to 0, I could divide by -1. And I would still get x to the third equals 0. That means one of my zeros is going to be 0, but that degree tells me that it's happening 3 times. So I would write 0 mult 3. Okay, when I set this second factor equal to 0 and solve, I'm going to get that x equals a -3. So that's another one of my roots. And when I take this third factor and set that equal to 0 and solve, I'm going to get that x equals a +3. Okay, so those are going to be our zeros there. Now we want to find the y-intercept. And again, we can plug that y-intercept into the original, or we can plug it into the factor. That's up to you. But I'm just going to go ahead and plug it into the original. So it'd be -0 to the 5th plus 9 times 0 to the 3rd, which that would just be 0 plus 0, which is 0. Oh, that looks weird. So our y-intercept is 0, 0. And we should also be able to see that because 0 is listed as one of our zeros for our roots or x-intercepts. Okay, and now we're doing end behavior. So I know we took out that negative when we were factoring, but when we do end behavior, we're going to use that original term with the negative, so the negative x to the 5th. So we took out that negative to help us factor a little bit easier, but that's not going to change what we use for our end behavior. So we use negative x to the 5th. So that negative tells us that our right side is actually going to be going down. And that 5th degree tells us that our left side is doing the opposite because it's odd. So our left side's actually going to be going up. Okay, so the way we would write this is the limit as x approaches -infinity. That's our left side. We're going to infinity, we're going up. And the limit as x approaches a positive infinity, f of x is going to be approaching a -infinity because our right side is going down. And again, we don't have any limitations here, so our domain is going to be -infinity to infinity. And now we can graph. So we'll draw a little rough sketch. We'll plot. I changed my mind. Okay. We'll plot our zeros. So we'll plot 0, 0. We'll plot a -3. And we'll plot a +3. Okay. And then we'll double check our y-intercept was 0, 0. Okay, that is meeting up with the other y-intercept I kind of already had. We should only have one y-intercept happening. So if you get something like 0, 18, you've done something wrong. Okay, so you need to make sure you're just having that one y-intercept whenever you graph. And then our left side is starting up. So it's starting up, it's coming through that -3. There's no multiplicity there, so it's just going to come straight through. And it's a little straight through. Okay. But then we have a multiplicity at 0, and it's a multiplicity of 3. That means it's an odd, so we're doing a shwoopa. We're flattening out, and we keep going. Okay, so again, whenever we have that odd multiplicity of 3, we come down, we approach it, we flatten out a little, and then we go back up. Again, we can call it a shwoopa if you would like. So it looks something like that. Doesn't have to be perfect, just as long as it's not like that. That's incorrect. Okay. Okay, we change our concavity, and then we have to come back down and go back through that +3 in order to complete our graph. And again, we're going to want to double check our end behavior happening there. Left side's going up, right side's going down. We're going through all those points we need. We plotted our multiplicities correctly, and that would be our graph. Okay, so I would make sure you go back through these graphs. It also may be beneficial to do some of the graphs on the review we had a few days ago because those solutions should be posted, and I think that would be very beneficial. Okay, now we're going to divide using some long division, everybody's favorite thing. So in order to divide using long division, we're going to use the box. Okay, so what we're dividing by, which in this case is 9x plus 2, it's going to go on the side. Okay, so then we take our first term, this, the 81x to the 3rd, and we're going to put it here. Okay, so that's always going to go in that first box. So then we say, what does 9x need to multiply by to get 81x to the 3rd? Would have to be 9x to the 2nd. And we can double check that. 9 times 9 is going to give us 81. X squared times x will give us x to the 3rd. Okay, so once we do that, we multiply that by 2 in order to fill out this bottom box, which would give us 18x squared. Okay, so we're good there so far. That finished out our first kind of row. And then we move on to the next one. So now we want these two on this diagonal. We want that to add to the next term of negative 27x squared. Oh, words. So this needs to add to negative 27x squared. So we add along those diagonals. So in order to do that, in order to add to a negative 27x squared, we would have to be adding a negative 45x squared. Please make sure that whatever's in this little diagonal, that those are like terms. They're like terms because they both have an x squared attached. If they're not like terms, you've done something wrong. Okay, so that has to add to a negative 27x squared. Okay, and we can double check 18x squared plus negative 45x squared is negative 27x squared. So we're good there. And then we say, okay, what does 9x need to multiply by in order to get negative 45x squared? So that's going to have to be a negative 5x. And we can double check that. Negative 5 times 9 is negative 45. X times x is x squared. And then we multiply that to that too. So that would be negative 10x. And we continue this process. Okay, so that finished that block. Okay, so on the next diagonal, these need to add to that next term, which is a negative x. Okay, that's coming from right here. Okay, so negative 10x plus a positive 9x would add to a negative x. So we're good there so far. Okay, so 9x times what would give us 9x? It would just have to be a regular 1. And then 1 times 2 is 2. Okay, so what we just took out was a constant. So that means that once we take out a constant, that's the last thing we can really take out of this that will divide nicely. So everything from here on out is going to be a remainder. So we still have to finish this out because these two still need to add to that last number of negative 2. Okay, and so this number would have to be a negative 4. And this last column right here, once we do that, this last entire column, which I'm going to change colors, this is our remainder. Okay, so we just have one number in our remainder. And now we just need to write out our answer. So we take what's on top, what's up here, which is 9x to the second minus 5x plus 1. And then we add onto that the remainder, which is negative 4, divided by what we were dividing by, which is 9x plus 2. I would also accept 9x squared minus 5x plus 1 minus 4 over 9x plus 2. Both of those are correct. Okay, and so that's how we would solve that long division problem. I would definitely go ahead and practice more long division. We have more on that one worksheet, but this is a good example. Okay, and we'll do B now. So this is what we're dividing by. We're going to put that on the outside of the box, but we don't have an X term, so we have to include a placeholder here. Okay, so we have to include a placeholder there and a 2. So make sure you are including those placeholders because that is going to make this impossible to do. And again, we repeat our process. So we start with our highest degree term, that's 3x to the 4th, and we put that right here. And we say, okay, what do I need to multiply x squared by to get 3x to the 4th? Well, that would be 3x squared. Okay, and then we go ahead and we multiply that out to everything else. And again, we can double check. 3x squared times x squared would give us 3x to the 4th, so we're good so far. So 3x squared times 0x, you can either write this as 0 or you can write it as 0x to the 3rd. Both would be correct. It doesn't really matter. That's totally up to you. Okay, and then 3x squared times 2 would give us 6x squared. And that's going to finish out that row. Okay, so now we go to the next diagonal, which is this one right here. And that's going to need to add to a negative 5x to the 3rd. Okay, so in order to add that to negative 5x to the third, this would have to be negative 5x to the third, because 0 plus negative 5x to the third is negative 5x to the third. So x squared times what would give us negative 5x to the third? Well, that would have to be just a negative 5x. Okay, and again, we can check that. Negative 5x times x squared is negative 5x to the third. So we'd multiply this. So negative 5x times 0x would be, again, 0. You can leave it as 0, or you could write it as x squared for continuity purposes. That's up to you. And then negative 5x times 2 is a negative 10x. And that will finish out that box. Okay, now the next diagonal, which is this whole thing, has to add to, and pause for a second, because a lot of people are going to want to say, oh, that has to add to 4x. But that's not possible because these are x squareds. So how would x squareds possibly add to just a normal x? And that's because in here, there's actually a placeholder of a 0x squared. So this actually has to add to 0x squared. Okay, so please be very, very careful of those placeholders in there. There's no way that this could add to 4x. It has to add to 0. So right here would have to go a negative 6x squared, because then this diagonal would add to 0. Okay, so then x squared times what would give us negative 6x squared? Well, that would be a negative 6. And we can go ahead and multiply that out. So negative 6 times 0x would be 0x. Again, you can just write it as 0 or 0x, it doesn't matter. Negative 6 times 2 is going to be a negative 12. Okay, and we just took out a constant, so that means everything from here on out is just about our remainder. Okay, now we can look at this next diagonal. And this has to add to that next term of 4x. And that will work because this diagonal is just regular x's. So negative 10x plus 0x is negative 10x. So we would have to add a 14x to that to get a positive 4x. Okay, I can't multiply x squared by anything to get a 14x. Well, anything that would work well. So this is part of our remainder. We're not really worried about anything else. And then we would find the rest of this problem by doing this diagonal, which needs to add to that negative 6. So we'd have to add a positive 6 to 12 in order to get this equal to a negative 6. Okay, and again, once we take out that constant, everything that's left over is our remainder. So this entire column right here, this is our remainder. Okay, and so the way we write our solution is we're going to write what's on the top. So 3x squared minus 5x minus 6 plus that remainder, which is 14x plus 6, divided by whatever we would be dividing by, which is x squared plus 2. And so that would be our solution. So make sure you're writing it like that. Some people tried to revert to the original. Please don't do that. Make sure you're looking at what's happening on top of the polynomial box. Okay, now let's move on to a slightly easier division. I would recommend going back and practicing some more long division problems. There's a ton online. You should have a packet or a piece of paper with some questions on there, and I think that would be beneficial. Okay, synthetic division. So when we're dividing by synthetic division, we can only do this when it's in the form of x minus c. Okay, so when it's synthetic division, we're actually taking the opposite of this number to plug in. And the reason we're doing this is because technically we're plugging in x and we'd set it equal to 0, so x equals 2. So that's why we're plugging in 2. Okay, again, can only work in the form of x minus c, so we take the opposite sign. We're plugging in a positive 2 here. Okay, and then we take our coefficients. So this x to the fourth has a coefficient of 1. This x to the third has a coefficient of -1. This x to the second has a coefficient of 7. This x to the first has a coefficient of -9. And this x to the 0th has a coefficient of -18. So those would be our coefficients. And then we're going to go ahead and divide. So we always bring down our first number, which is 1, and then we multiply 1 times 2, which would give us 2. Then we add straight down. So -1 plus 2 is a positive 1. And we repeat 1 times 2 is 2. We add straight down there. Okay, so that's going to give us 9. 9 times 2 is 18. We add straight down there in order to get a positive 9. And then 9 times 2 is going to be a positive 18. And we add straight down to get 0. Okay, so this one actually divides nicely, which is kind of nice. And the way we would write this is we drop down a power from our original. So in our original, our highest degree power was to the 4th. It's now going to be to the 3rd, and we use these numbers as our new coefficients. So it'd be 1x to the 3rd, again, we drop down a power, plus 1x squared, plus 9x, plus 9. And we don't have a remainder because this divided nicely, but if we did have a remainder, say here, because I just want to give us some practice with this. Say instead of getting out 0, I messed up, I did a negative and I got, -36 instead. The way that I would write this is plus, you can say -36 over what we were dividing by, or you could write it as, again, x to the 3rd plus x squared plus 9x plus 9 minus 36 over x minus 2. So we write that remainder the same way we would in those previous long division problems. I just wanted to show an example of this. Again, this one actually did divide nicely, but if it didn't, this is how we would write that remainder. So I'm going to change that back just so I don't confuse anybody. This is 0. Okay, so make sure you're not forgetting that remainder on synthetic division. Okay, so now this asks us to factor the polynomial completely given the binomial factors. So starting with this first one, we are going to use synthetic for this because both of these are in x minus c form. So that makes our life a little bit easier. So starting with the first one, because it's in x minus c form, I'm actually plugging in the opposite, which would be a positive 1. Okay, and now I'm going to take my coefficients. So to the 4th, I had a 2. The 3rd power has a coefficient of -9. The 2nd power has a coefficient of 2. The 1st power has a coefficient of 9, and the 0th power has a coefficient of -4. Okay, so I'm going to drop down the 2 as always. And then I'll start my process. So 2 times 1 is 2. And I'm going to add straight down. So that will give me -7. And then -7 times 1 is -7. So that's going to be -5. -5 times 1 is going to be -5. We'll add straight down to get 4. And 4 times 1 is 4. We'd add straight down to get 0. Okay, so what this 0 is telling me right here, because this divides nicely, this is telling me that x minus 1 is a factor. Okay, and that these would be my new coefficients, which is great, but this said factor the polynomial completely. So, and it gave us that these are binomial factors already. So really this isn't telling me anything because it already gave me that this was a factor. So now I'm going to take those coefficients I just got and I'm going to keep going. So now I'm going to use this x plus 1, which is also an x minus c form. And now I'm plugging in a -1. Because again, we're taking the opposite for that. And I'm going to use these numbers as my new coefficients instead of rewriting it again. So I'm going to drop down that first power that first number as before, which is a 2. And then I do 2 times -1, which would give me -2 right here. And then I'll add straight down. So when I add straight down, that's going to give me -9. -9 times -1 will give me a +9. I'll add straight down, which would give me a +4. And 4 times -1 would be a -4. I add straight down and I get 0. okay? Remember in the last one, this 0, this is a remainder, so I'm not going to include it in my new, in my new division. Even if I did, if I put 0 here, it would add to 0 again. So it really doesn't matter all that much. But you don't really need to include it because that's your remainder and it divided nicely, so we wouldn't use that. So now because I did this twice, instead of dropping down 1 power, I'm going to drop down 2. So we already have one of our factors is x minus 1. That came from that first set of division. And x plus 1, that came from that second set of division. So now I'm going to take these, and these will be my new coefficients of the third factor here. So I did it twice, and my original degree was 4. So I'm going to drop down 2 powers because I did it twice. So it'd be 2x squared minus 9x plus 4. Okay, and again, this said factor completely, so I got to get it all the way down. So in order to do that, I am going to use the box. Okay, so I'd have 2x squared and 4. So it needs to multiply to an 8x squared, but add to a negative 9x. That's going to be negative 8x and negative 1x. Out of the first column, I can take out an x. Out of the second column, the closest box is negative, so I'm taking out a negative, and both of those are divisible by 4. Out of the first row, those are both divisible by 2x. And out of the second row, the closest box is negative, so I'm taking out a negative. And what they have in common is a 1. So I can write this as x minus 1, x plus 1, x minus 4, 2x minus 1. And that would be my full factored form. Okay, so we're done with that problem. And we're moving on to the next one. Okay, so the next one tells me that x plus 3 is a factor. Again, this is an x minus c form. So what we're actually plugging in is a negative 3. Okay, and I'll take my coefficients. So I have a coefficient of the x third of 1. The squared term is negative 3. The first power term is negative 13, and the constant term is 15. So I'll drop down that 1. Okay, and then I'll do 1 times negative 3, which is negative 3. And I'll add straight down to get a negative 6. Negative 6 times negative 3 is a positive 18. And I'll add straight down to get 5. And then 5 times negative 3 is negative 15. And I'll add straight down and get 0. Okay, so by doing this, I'm factored out that factor of x plus 3. And again, this time I only did it once, so I'm only going to drop down 1 power from my original. So my original was 3, so this will be x squared minus 6x plus 5. And again, those coefficients are coming from right here after I divided. But again, it said factor completely, so I'm going to put this in the box now in order to factor it all the way out. So I need something that multiplies to 5x squared, but adds to a negative 6x. So that's going to be negative 5x and a negative 1x. Out of the first column, I can take out an x. Out of the second column, the closest box is negative, so I'm taking out a negative. And both of those are divisible by 5. Out of the first row, I can take out an x. And again, on the second row, the closest box is negative, so I'm taking out a negative 1. So I'd write this as x plus 3, x minus 5, x minus 1. And that would be my answer. And that is factored completely. And we know it's factored completely because we don't have any exponents left over. So when everything has an exponent of 1, that's how we know we factored it as far as we can. Okay, and we're getting to the end, kind of. Okay, moving on to the next one. So we're using the remainder theorem to evaluate f of c. So this time it's giving us what c is already. This isn't in the x minus c form. It's already giving it to us. So we're really plugging in negative 3 already. We're not changing the sign here. So whenever we use the remainder theorem, we do not change the sign. We change the other signs because those are factors rather than being given a number to plug in. We're just being given the factors. We have to use the opposite number to plug in. Here we already are given the number to plug in. So let's go ahead and do this. And we're going to use synthetic for this because that is what the remainder theorem deals with. So our fourth degree term has a coefficient of 1. Note we don't have a third degree term, so that would technically be 0x to the third. So we have to put a placeholder of 0 in there. Our second degree term is -10. Our first degree term is -2, and our constant term is 4. And then we can go ahead and solve this. So we bring down the first to get 1, and we'll do 1 times -3, which is -3. Then we add straight down, so that'll give us -3. We'll do -3 times -3, which is a +9. We'll add straight down to get a -1. We'll do -1 times -3 to get a +3. We'll add straight down in order to get a +1. And we'll do 1 times -3, which is a -3. And again, we'll add straight down to get 1. So what the remainder theorem says is that when we're plugging in something like -3, f of -3 is equal to whatever that remainder is of 1. So instead of plugging in -3 and trying to solve this out the way we maybe have done it previously, we use synthetic in order to find that remainder. And that remainder is the same as f of -3, the same as if we had just plugged it in. And this is how we would write our solution. So please make sure that you are doing that. Okay. So again, remainder was 1, so f of -3 is 1. Okay, now this one asks us to find k such that this equation has a factor of x plus 1. So this is in the x minus c form, which means we can use that synthetic division, but instead of a +1, it would be a -1. Again, when it's in x minus c form, we do the opposite sign. When it's not, we don't. Okay, and now we're going to list out our coefficients. So the coefficient of the first one is k. Coefficient of the second is -1. Coefficient of the third is k. And coefficient of the last one is -3. We didn't have any placeholders we needed to include, so we're okay so far. So I'm going to show 2 ways to do this. And I think one is more complicated than the other, but it's up to you. So the first way we would do this is just operating with k as if it was just a number. So we'd bring down k, and we do k times -1, which would be -k. And then we add straight down. So we would have -k minus 1. Okay, and then we would multiply that times -1, which would give us a +k plus 1. Then we would add those straight down to give us 2k plus 1. We'd multiply that by a -1, which would give us -2k minus 1. We'd add straight down to get -2k minus 4. Okay, and if this has the factor of x plus 1, that means that the remainder is 0. Okay, so then we would take this -2k minus 4 and set it equal to 0. So we'd add 4 to both sides to get -2k equals 0 or equals 4. And then we divide both sides by -2, and we'd get that k equals a -2. That's one option. The other way we can do it is set it up the same way. But I typically try to approach it more of it as a puzzle. And I work forward as far as I can, and then I work backwards as far as I can. So really, there's not much to work forwards towards. I know I'm going to have to bring this down. I know it's going to have to be k. So I'm going to start by actually working backwards. So I know my remainder has to be 0. So if my remainder is 0, I know that this is going to have to be a +3. Okay, because that's the only way I'm going to get 0. Sorry, it's a -1. Okay, I know that if that is a +3, then this would have to be a -3. Okay, right, and we can check this. -3 times -1 is +3. Okay, we're doing okay so far. So that's my working backwards, but then this column doesn't really help me. So I am going to work forwards a little bit with k, and we'll see where that takes me. So if I brought down k, okay, and k times -1 would have to be a negative k. Okay. And then negative k plus a -1, this would be negative k minus 1, sorry. And again, this would be a positive k plus 1. So that means that 2k plus 1 has to equal a -3. So we'd subtract 1 from both sides. We'd get that 2k equals a -4. Divide both sides by 2 to get that k equals a -2. So either way you spin it, you're going to get the same thing. It's more difficult because we have two k's happening in this problem. The working forwards and working backwards works a little bit nicer when, say, like we were already given this k value, and we just had to find one. The working forwards and working backwards kind of works out pretty nicely. But this first method will always work. And you just work as far forward as you can, and you essentially use equations rather than just using specific numbers. So it's up to you which one you decide, but that's how you would go about doing that. The big thing you need to know is that if x plus 1 is a factor, that means that when we plug in -1, the remainder would have to be 0. Okay, moving on to solving the inequalities. So the big thing about solving an inequality is that it has to be equal to 0. Or well, not equal, but it has to have the inequality symbol and then 0. So to do that, we're going to first start by taking this first equation and subtracting 15. So we'd have x squared plus 2x minus 15 is less than or equal to 0. Okay, the next thing we're going to do is factor this. So it's 3 terms. There's no GCF. So we'll go ahead and put it into the box. So that would be x squared and -15. So we need something that multiplies to a -15x squared, but adds to a positive 2x. So the two numbers that are going to do that are 5x and -3x. So out of the first column, you can take out an x. Out of the second column, you can take out a 5. Out of the first row, you can take out an x. And out of the second column, the closest box is negative. You take out a -3. So this factors to x minus 3, x plus 5. From there, we need to figure out what our zeros would be. So the way we do that is actually by setting these equal to 0 and solving. So one of our zeros is going to be a positive 3. And one of our zeros is going to be a -5. Hopefully you can see that just kind of by looking at those factors. And then we need to figure out what this problem is doing. So our leading term is actually x squared. So that means that it's positive, so our right side is going up, and it's even so that our left side is doing the same. So a really rough sketch of this graph would look something like this. Okay, and so over on the left, this is a positive interval, this is a negative interval, and this is a positive interval. And so we are looking actually for something that is less than or equal to 0. So we're actually looking for that negative interval. So our solution to this would be bracket, because it's or equal to. So bracket -5, 3 bracket, because that is the negative interval. And so that would be our solution. Okay, moving on to the next one. Again, first thing we have to do is get it set equal to 0. So we're going to subtract 2x squared from both sides. Okay, so, and we're going to add 5x to both sides. I'm going to do both of those in the same step. So that would give us x to the third minus 6x squared minus 16x is greater than 0. Okay, because I did this to get 0 on one side. Okay, so the next thing we check for is a GCF, and I can actually take out an x here. So that would leave me with x squared minus 6x minus 16. And now I have 3 terms inside those parentheses, so I can use the box here. So I have x squared and a -16. So that's negative, it has to multiply to a -16x squared, but add to a -6x. Hopefully we can look at this and see that it should be -8x and a positive 2x. So out of the first column, I can take out an X. Out of the second column, the closest box is negative, so I'm taking out a negative, and both of those are divisible by 8. Out of the first row, I can take out an X, and out of the second row, I can take out a positive 2. So this entire thing factors to X times X minus 8 times X plus 2. Please do not drop that GCF. That is so important. Hopefully we can look at this and see that our zeros are going to be from this first one, it'll be 0. From the second factor, it'll be a positive 8. And from this third factor, it will be a negative 2. And we'd plot those on our number line. Okay, and I got those zeros by just setting each of those factors equal to 0 and solving. Then I determined my end behavior. So my highest degree term is x to the third. It's positive, so that means my right side's going up. And it's odd, so my left is doing the opposite. The left is going down. So my graph would look something like, oh, that was bad. Something like this. So this is a negative interval, this is a positive interval, this is a negative interval, and this is a positive interval. And I'm looking, so then we have to double check, where am I looking? I'm looking for something that is greater than 0. So I want the positive intervals. So that means my solution is going to be parentheses, because I'm not looking for greater than or equal to, it's just strictly greater than. So parentheses -2, 0, union, parentheses 8 to infinity. Because those are the two intervals where my graph is positive. And that would be my solution. Okay, so this next one asks us to list the zeros, extrema, absolute or relative, and max or min. So starting with this first one, we'll start with our zeros. So our zeros occur when x is equal to 0. So that's happening, I'm sorry, y is equal to 0. So that's happening here, 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 and here. So our zeros are, I don't need parentheses, we can just list them out. -1.51, it's right here. -0.468, it's coming from right here, this point. 0.468 is coming from this point, which is happening here. And positive 1.51. It's right here, and it's this point. Those would be my zeros. Okay. Then I guess we could do maximums. And so I have a maximum that's occurring right here. However, it is not the highest point on this entire graph because the graph is going up still. So we can call that a relative max of the y value, which is 1. And we say it occurs at x equals 0, because that's what the x value is. Okay, and so that's how we would write that. I also have some minimums occurring, and this is a little tricky, right? Because I have two minimums, and they're both technically speaking the lowest points on the graph. However, you cannot have more than one absolute minimum or absolute maximum. So because there's technically two that are the lowest point on the graph, one doesn't beat out the other. So both of these would be relative minimums. So we would say for this first one, this one right here, we would say it is a relative min of the y value, which is -2.125 at x equals -1.118. And so that's why it's important to specify the at, because technically you could have two relative minimums that have the same value, but occur at different places on our graph. Because we also have this relative minimum over here with this point, that is a relative min of the same value, -2.125, but it's actually occurring at x equals a positive 1.118. And so that's how we would list our zeros and the extrema, which is the extrema are the maximums and minimums. Okay, going over to our ratchet graph, which is what this is. I drew this. I'm doing great, guys. It's a little rough, but it's fine. Again, we're going to start with our zeros. So 1 0 is occurring here. That's happening at negative 9. Ooh. 1's occurring right here. That's negative 5. Another is occurring right here, which is a positive 1. And we have another right here, which is a positive 3. So those are all my zeros. The next thing we want to do is list maximums and minimums. So I have a minimum that is happening right here. And this is actually the lowest point on the entire graph. So this is actually an absolute minimum. And that absolute min is negative 6. And it's occurring at x equals a negative 7, right? Because this is the point negative 7 comma negative 6. So again, the y value is the absolute minimum value, and it's occurring at that x equals. Okay. So next we have this point right here, which this is actually a relative max. And so what you need to note about this is even though it looks like the highest point on our whole graph, we have these arrows, so our graph is going to keep going up. So this is not the maximum, the absolute maximum of our graph, because there are values that will be higher on it as these arrows keep going up. So this is a relative max of 10, that's the x value, at x equals negative 2. Okay, and again, this is the point negative 2, 10. So that y value is the maximum value, and that x value is where it occurs. Okay. Then we've got one more that's happening right here. And so this is a minimum, but it's not the lowest point on the whole graph. We already listed that. So this is actually a relative min. And that relative min is negative 3, but it's happening at x equals a positive 2. Right, and we should see that because again, this is the point of 2 comma negative 3. But it's not the lowest point on the whole graph, so that's why it's relative. So one big thing to reiterate from these two graphs is you can only have one absolute max and one absolute min. You can't have two absolute maximums or two absolute minimums. One of them would have to be relative, or both of them would have to be relative. So just make sure you're being careful with that. We're getting towards the end. Okay, so now we want to indicate which intervals our graph is increasing, decreasing, or constant. So the way I think about this is I think about a little man walking on my graph. And if he's going downhill, he's decreasing. If he's going uphill, he's increasing. If he's walking on a flat surface, he's constant. And that's how I think about it. The other thing that has helped some of my students is to draw, because they want to write the y values whenever they're writing the intervals of increasing, decreasing, and constant rather than the x's. So what's helped some people is to draw vertical lines where the graph changes its direction or changes its its behavior. So like we're changing from decreasing to increasing here. We change our graph again right here. And we change our graph again right here. Okay. The other thing we want to note is on all of these intervals, we're always going to be using parentheses because you can't increase, decrease, or be constant at any of these specific points, especially when it's changing. So we start on this first interval. So over here on this side of our graph, our little man, he would be walking downhill. And so because he's walking downhill, that's actually an interval of decreasing, which I'm going to just write as D. And so that's happening from negative infinity to where it changes on this first line right here, which is happening at 0. Okay. Then our little man starts to walk uphill, right? He's right here. He is walking uphill now in this middle interval, this one right here, which is happening between 0 and 1. So we are increasing between 0 and 1. Okay. On our next interval, our little dude, he is just walking a flat line. And that's happening on the interval between 1 and 2, because that's where these lines are crossing. So we are constant from 1 to 2. Okay, and in our last kind of interval that occurs here, which is over here, our little man would be going up the hill. Okay, so he is increasing again, so we union from 2 and on until infinity. And so that would be our behavior. So if the lines help you, that's great. You can use those. If not, totally understand. You do not have to use them. It's just a thought so that we can focus on where our graph is changing and the fact that those should be in relation to the x values, these values where it crosses, rather than the y values. Okay. So moving on to our next graph, again, I'm going to draw the vertical lines where the graph changes direction. You do not have to. So we change direction here, and we change direction again right here. Okay, so in our first interval on this left side, that's over here, our little man would be walking downhill, so he is decreasing from negative infinity, and then our graph changes at a -1. Again, we're using parentheses for every single one of these, because we cannot increase or decrease at a specific point, even if it's contained in the graph, doesn't matter. In this middle piece, our little man, he is walking uphill, so he is increasing from that -1 to that +1. And then he decides to change his direction again, because then he starts going back downhill from that +1 and on to infinity. And for constant, there is none. He decides not to walk on a flat line. And so those would be our correct intervals. So again, if the lines help you, you can use them. If not, I understand. So use a table to determine which consecutive integers the real zeros of f of x are located on the given interval. So if we think about this graphically, zeros would have to occur when we have a negative y value and a positive y value, because if we connected them, they'd have to cross that graph at a 0, right? So we want to look at where our y values change from positive to negative or negative to positive. So that's happening here, which would be happening between 4 and 5. So zeros occur, oh, no, can't spell. Occur between 4 and 5. Okay, and then this happens again between -1 and 6, but that's actually happening between the numbers of 6 and 7. Okay, oh, so we look at the y values to determine whether they're changing positive to negative or negative to positive, but when we list those intervals, again, we list them as the x values. So looking at B, we should hopefully see, okay, we're changing positive to negative here. So the zeros occur between, again, we use the x values there. So -1 and 0. Okay. This happens again right here, and that's happening between 1 and 2. And then it occurs just one more time right here, which is happening between 3 and 4. And that's all I'm looking for on those questions. And finally, what makes a graph a polynomial function? It must be continuous. It's one big part of the definition. And have no sharp turns. So it has to be continuous and smooth, no sharp turns there. And so that should finish us out for the review. So again, this is a good review, but I would definitely review previous quizzes, previous reviews. And please know that anything up until this point in the year is always fair game on a test. Hopefully this helps. Y'all have a great day.